All right, everyone. So welcome to our next session here on incorporating physics into deep models with implicit layers. This talk is going to be given by Zico Kolter. So Zico is an associate professor in the computer science department at Carnegie Mellon University, and also serves as chief scientist of AI research for the Bosch Center for Artificial Intelligence. His work spans the intersection of machine learning and optimization, with a large focus on developing more robust and rigorous methods in deep learning. In addition, he has worked in a number of application areas, highlighted by work on sustainability and smart energy systems. He's a recipient of the DARPA Young Faculty Award, a Sloan Fellowship, and Best Paper Awards at NeurIPS, ICML, Honorable Mention, IJCAI, KDD, and PESGM. So Zico, take it away, and thank you so much for coming.
All right, thank you, Priya. Okay, let me see. Let me share my screen here and see how this works. Let me actually first set up the windows to do this properly. Okay. I want to share the screen. I'm almost certainly going to get this wrong and end up sharing my slide view in a second, but let's, so can you all see an empty desktop right now?
Yep, we see a dune.
Okay, perfect. The lovely default background of. All right, and now, do you see the full slides, or do you see like my presenter view?
No, it looks good.
Okay, it looks good. All right. Well, everyone, thank you very much. It's wonderful to be here. I'm going to talk today about some of our work we've done on actually modify the title a bit to make it broader. So incorporating both physics and decision making now into deep models. So it wasn't enough to just do one of those. I want to talk about doing both of them. Incorporating physics and decision making into deep models using implicit layers. So this is going to be joint work with some of my students, including Priya here. I liked her reading my bio in a very formulaic way, but I interact a lot with Priya, of course, so I'm actually studying some of her work here, as well as some other students, Philip and Brandon, our former student Brandon, and then actually several other collaborators at other universities. So we have some joint work with people from MIT in this case, and also at Stanford. All right, so just give kind of a brief outline. I'm going to talk first a little about machine learning. Again, this is going to be very high level. You know, what does machine learning do? And what is it not so good at so far? And then I'm going to talk then about this sort of, not new framework, because this is going on in a lot of different aspects, but this sort of less common framework of using what we call implicit layers in the context of deep learning. So I'll talk about what that means and sort of how we solve problems like that. Then I'll talk about some applications of using implicit models in deep learning. So this has to do with things like learning with differentiable physics, and then finally incorporating decision making into deep models. And I'll end with some final thoughts. So first of all, let me talk a little bit about machine learning and you know, maybe not why we're all here, but maybe why this field has exploded so much in recent years. So it's sort of undeniable how cool some of the things we can do with machine learning is these days. So, you know, we can make pictures of pretend people. We can make up stories about unicorns that don't actually exist. We can solve games like StarCraft. And this is your sort of, you know, I want to highlight two things here. You know, I want to highlight just how cool all these things are. I mean, I thought these faces were a joke when I first saw them because they look so realistic. I thought people were like, oh, look how good AI is, and just showing real pictures. But no, those are actually generated faces for these things. And so these are sort of amazing things to be able to accomplish from AI systems. But at the same time, if there's sort of one common theme about these different things we've done, and many other domains too, it's that they largely exist kind of in the virtual world, right? These are sort of, you know, pretend faces you're making. It's games we're playing that are sort of virtual games. It's pretend text, things like this. And if you get it wrong or things don't really work that well, it's not that big a deal. But of course, what we actually care about is much more than that. What we actually care about are, the build is wrong here. What we actually care about are applying these things to real world problems, right? What this workshop I think cares about, and frankly, what I think actually excites people about AI is not just the fact that we're, you know, generating cool pictures and beating a lot of video games. It's the promise that these things have when we deploy them to the real world. And so be it domains like autonomous driving, be it things like climate models and climate decisions, or be it things even as simple as just basic manipulation that we can do with objects, maybe say at the level of a toddler, which we're still very far away from. These are the things that I think people get really excited about when it comes to AI. And of course, the question is, what are we missing between what we've done so far? I think it's also apparent to everyone that we're not yet at a place where we've succeeded kind of in having AI revolutionize all these physical fields too. So what are we really missing to bridge this gap here? Why has AI not made the leap to the real world yet? And one thing I would say about all those systems, be it autonomous cars, be it about simple manipulation, or be it about going to things like models of large scale climate effects, is that a lot of these models are essentially based upon some physical dynamics or physical principles, right? So the rules of the world are not arbitrary. Things evolve in certain ways, sometimes in very well understood ways. And we know that these physical laws underlie and govern kind of the real world. But yet when we do kind of silly things like slap a neural network in these systems to try to predict what's going to happen, things can go very, very wrong here, right? So if we're just trying to use a generic deep network to say predict how physics will evolve to steer a car, if we're going to use a generic neural network to predict how some sort of climate model will evolve, these things don't often work as well as we hope, because they don't generalize as well as we would like to these new scenarios. And this is a big problem with their application to these sort of real world and frankly kind of high stakes domains. What could possibly go wrong, right? What's the worst thing that could happen if we just do try to throw deep networks at these systems? And like I said, they oftentimes don't. Deep networks can have a very hard time capturing some of the things we understand very well about existing systems. But the flip side of this that I would sort of emphasize here is that there's a lot of things that our deep networks have a hard time capturing, but which to a first approximation are actually quite well understood, right? So, we actually understand physics pretty well. I mean, maybe, we can't always model it that well, but we understand the basic laws of Newtonian mechanics, we understand the basic laws of fluid dynamics, things like this, that really do govern the world that we see, that we interact with, and that we would like to try to incorporate into our models. And so the basic idea of this talk, and this is actually going to apply both to the decision-making part and to the physical modeling part, is that the way forward that I, and not just me, but that myself and many others are kind of thinking about these days, is that we would like to try to embed this known structure into our networks, right? So we want to take this sort of generic network and kind of, take that apart a little bit and say, well, maybe we actually want to require that one of these layers in the network, or maybe the last layer or something like this, actually corresponds to some well-studied and kind of known input-output mapping, say a rigid body simulator, or a fluid dynamic simulator, or maybe a decision-making based or an optimization-based decision-making problem. Okay? And this sounds great, right? Of course we want to do this. Of course we want to integrate constraints and sort of knowledge into our deep networks. But the bigger question is, how do we actually do this? How do we actually go beyond just sort of thinking about this and actually make this a reality? So this talk is going to be kind of a whirlwind tour of some of the ways in which we've gone about integrating these kinds of hard constraints and hard sort of known knowledge into deep networks as a way of making them both more kind of interpretable at a high level, but also just perform better with much less data, ideally on domains that are of eventually going to be sort of mission critical, where we have to get it right every time. So that's the high level view, or that's the high level message of this talk. Okay, so let's jump into some of these things. Now, the question arises, of course, is how do we do this? How do we actually incorporate a constraint like this into a deep network? And the tool we're going to use is a tool based upon what I'm calling implicit layers or implicit models in deep learning. What's the basic idea here? The basic idea here is that we think of most deep networks as being largely unstructured things, right? Maybe a little bit more structured than, say, this fully connected network you have on the left here. But the basic idea of most machine learning, and I'm going to talk about this at a high level for now, but I'll get, I will have some math in a few slides, but then try to give the main message here. But the basic idea here is that, we have some inputs, we feed it through a network, we get some outputs, but for the most part, most deep networks don't enforce hard constraints on this process, right? They just say, here's some convolutional mappings, here's some linear mappings, here's some other layers that we put together like transformers and things like that, and the output is kind of whatever it is, and we're just gonna use enough data to train it to do what we want to do. In contrast, I'm gonna think about models where a certain layer does in fact have very hard constraints about what it does. So a certain layer will actually not be a generic kind of tool that can do anything, but it actually does something very specific and actually does something very intentional in its computation. So for example, some examples of this would include things like you can incorporate an optimizer there, you can incorporate like a controller in there, a physics engine, a game solver, a SAT solver. And in fact, not only is this sort of an interesting thing to do from a machine learning standpoint, it's also very lucrative. Lucrative is the wrong word. It's also very lucrative when it comes to publishing papers, because at this point, still you can basically take these different modules, plug each one into deep network and get another paper out of it still. Maybe we're going along that, maybe moving a little bit beyond that. But in my group, we've done actually a lot of work kind of making an industry out of this a little bit. We've done a lot of work in incorporating kind of different aspects of structured layers into deep networks to enforce different things that these networks can do. The big question, of course, is how do these things work? Like, is there a common theme that ties these whole things together? And actually there is, because it turns out that almost any structure you want to impose in a deep network. This is not always true, but for the most part, this actually holds for almost everything that we've considered so far. It turns out that if you have a lot of tasks like an optimizer, like a controller, like a physics engine, all these things, they reduce, and you have your input-output mapping here. So you have the input of the network X and the output of the network, which are the input of the layer X and the output of the layer Y. It turns out you can basically encode all of these constraints as what we call an implicit form layer. And the idea is that most networks, most layers in the network, they produce their output Y as some well-defined function of the input X, right? So Y equals a matrix multiply times X, or equals the ReLU of X, and things like this. When we move to implicit layers, this gets actually quite a bit more complex. Instead, we are talking about an implicit form layer, which has the form of finding a Y such that the joint combination of the input and output satisfy some nonlinear equation here. So, f of x and y equals 0. And I'll actually get a few examples of this in a second. So this actually is a very, very generic formulation that can capture a lot of domains. For example, physics can largely be expressed in terms of solving one of these implicit form layers. Optimization problems can also be expressed in this way. A whole lot of problems we really care about can be expressed in this form. And so it really is the case that this is a very, very sort of powerful paradigm, and it's one that lets us incorporate a lot of expressivity into our models. And I'll talk more about this, how we do this in a second. However, before I do that, I want to actually also stress kind of the main challenge that arises when we actually do this, because machine learning systems or deep learning systems are kind of entirely predicated on this notion of end-to-end training, usually with gradient-based methods, so like Backprop methods. And when you incorporate one of these implicit layers into a deep learning system, you need some way of actually still running Backprop or other things, other similar things, in order to actually train these models. And that at least seems to be a challenging thing. So how do we do that? Oops, it's supposed to be an animation here. Sorry, I'm hitting with a lot of math at once. This is supposed to build a little more slowly here. But let me just give it a high-level description here, and I'll still walk through it term by term. So when you have something like this, so suppose we have an equation. Oh, there it went. Oh no. Okay. When you have an equation like this, where my output of a layer wants to solve some nonlinear equation. The question is, how do I compute, for example, the derivative, or really the Jacobian, of my output y with respect to my input, and also with respect to the parameters of that layer, right? Like the parameters of the physics model or things like this. And this seems hard, right? I mean, you have this solution. How do I, you can solve this thing different ways, right? I can use an iterative method to solve it. How do I actually backprop through that? And fortunately, though, there actually is a trick that we have up our sleeve here to do this, which is actually not a new trick. This is called the implicit function theorem. It goes back many centuries to the beginnings of calculus. But the basic idea here is that even though this seems hard, it turns out there actually is a very well-defined way to compute backprop through one of these implicit layers. It basically, and I'll just sort of describe each step here. And again, the details are not important if this math is sort of not familiar to you. But the basic point here is that we can take this sort of solution that we get, and by the way, we solve these problems through whatever kind of means we want, right? However you solve normal physics simulation, however you solve normal optimization, you can solve it just that way. The challenge for deep learning is how you backprop through it. But when you have this, what you can do is you can say, take your solution here. You can actually, can people see my cursor? I'm curious to see where I'm pointing when I do this, or is it?
Yeah, we can.
Okay, so it helps a little bit. It's nothing like me standing in front of a board and pointing to things, I know, but it's the best thing we can do virtually. You have your solution here. You have, and then what you do is you actually differentiate this solution. So you differentiate the equations at the solution. You apply the chain rule one time to get this little breakout of this thing like this, and then you just solve. And then these two terms, this Jacobian here, this Jacobian here, are essentially given to you by basically existing software libraries like PyTorch and TensorFlow. Those are sort of known things that you have from your existing automatic differentiation tools. And the thing you don't know is this Jacobian of the output with the input, but now this becomes a linear system you can now solve. And so this seems like a sort of a very simple idea, but of course, and in fact, it is just implicit differentiation. It goes back many decades or really centuries. But this is actually a very, very powerful paradigm that lets us incorporate a very rich class of models into deep learning systems. So this is going to be actually a very, very powerful tool, and different domains such as, I'm going to show you a lot of examples of it, but also things like neural ODEs use this. A lot of existing models use this implicit differentiation to actually compute, to incorporate very structured layers inside deep networks. So I'm going to give a few examples of that soon. And again, don't worry too much if this math is a little bit complex. Hopefully some of the examples I give will kind of codify this. But for those that sort of are following along, I want to make one very important point here, which is that I'm not advocating to unroll solution procedures and then backprop through that. This is sort of a subtle but important difference here. So a common way of solving these things before is we'll say, well, okay, I know how to, the way I typically solve these things is, say, with an iterative method or maybe gradient steps and things like this. The way I'll backprop through that is I'll just kind of unroll my forward computation and then backprop through this unrolled graph of computation. And this can work, it works sometimes, but it's also really memory intensive. You have to store along every intermediate iterate, creates very long graphs that can sometimes cause instabilities, and it has a lot of problems associated with it. And so what I'm actually advocating for is something a little bit more mathematically, I think, nice here, which is that what you do when you want to have one of these implicit layers in a deep network is that you actually just find an exact solution any way you want to. So I run my normal physics simulator or on my normal optimization approach. And then I look at the solution, take that solution, and then use this theorem I wrote in the previous slide to backprop through it analytically. This is much more memory efficient. It's basically effectively free after computing a forward pass. And there are all sorts of sort of nice things about this overall approach. Actually, maybe, so now what the next two parts of this talk are going to do is going to give two applications of this sort of general idea here. One in the context of incorporating physics into deep networks, and one in the context of incorporating decision-making and optimization into deep networks. However, maybe before to make this a little bit more interactive, maybe I'll pause for questions right now in case there are questions, and then we'll kind of keep going after that if there are or not any questions. Oh, good. I'm already seeing notifications, so
Yeah,
open
so
those
one
up.
question is, and I can read them out to you, but
I actually got them. This is actually great. I'm going to look down from here when I do this, but it's actually true that I can see this pretty easily. So let me do one thing though, to make it a little nicer for me. Okay. All right. So I think I have them on my screen. So Tianlei Yuan asks, what if the physical model cannot be analytically solved? Right. So none of these. Here is actually. Maybe I'm not quite sure what you mean by analytically solved. But the important point here is that these sort of procedures here do not have to be analytic. In the meaning that there is some sort of form of y equals some function of x, right? These can be actually very sort of generic, and we can use existing very complex iterative solvers like CF body dynamics to solve these things. So the constraint of it being analytic is definitely not there. If they can't be solved at all, if you have no solution, yeah, that could be a little trickier. I'm not quite sure what you would do there, and that might be harder. But as long as you can solve them even in an iterative fashion, this same approximate, to within epsilon of being optimal, say, this same approach still works here. Lauren Coons asks, what if the physics model is computationally expensive? Does this help speed it up, or is it still a limiting factor? Right. So to be very clear, this is not about models. It's actually kind of about the opposite. So slowness of these models is a big problem, and it's one of the more sort of practical problems of doing this in practice. But I think this can be addressed to a certain extent. More people in some cases. We are not speeding up models. We are using models as they already exist in their potentially slow form. And in fact, we're putting them inside networks that require us to call these multiple times in, say, a training loop. So we're actually slowing things down a lot in theory. But the hope is that if we train networks in these ways for maybe models that are medium scale still, we actually can incorporate much more expressivity and power into our networks, and really not just power, but also sort of the right kind of approximations into our networks to accomplish what we want. Okay, I'm actually gonna put these. I might cover up my slides a little bit, but I'm still gonna put these on the slide itself. All right. Any other questions? So someone says, I'm familiar with climate science modeling. Can you be useful for more efficient parameterizing? And to be fair, I'm using climate models as an example. We haven't really done that. We've done some of this with PDEs in general, not with PDEs for climate models. This is more so far about climate making decisions that we've done with some of these things. That's more the second part. It's less about, yeah, I think maybe this relates to the next, but Kyle asked about efficient parameterizing, and then Wyatt asked about, yes, I'll run the physical model at inference then. So yes, you have to, the goal here is that the model itself incorporates the physical model inside of it. So at inference time, you still have to run the model. There are all sorts of ways around this, by the way, and doing this approximately is a huge subject that we are very actively working on. But this default formulation does require still running the model at inference time. So it's not about being more efficient. It's about having better models that incorporate some amount of learning. So if you're completely happy with your model, by the way, then you maybe just want to use your model. If your model does everything. But if you want to incorporate some kind of learning into your model, some sort of data-driven tuning of any kind that you would typically do with machine learning methods, this is a nice way of incorporating those constraints with the constraints that you have from your physical system. So hopefully that answered most people's questions there. I guess Kyle and Wyatt, I think, had similar questions. Okay, so 2 questions. Where do we go on from here? Maybe let me, and the code example is freely available. Yes, so I think that let me talk about where we're going to go in a second, and then yes, there's code on my group's website and other places too. I'll talk about those more in a second. All right, so let me give a few examples of this now. And the first one I'm going to give is about incorporating physics into deep networks. And in particular, we're going to incorporate physics, actual physics here, right? Like not just approximate physics, but actually building a physics simulator inside a deep network. So this is work that was from NeurIPS 2 years ago, or a year and a half ago, by my student Philip, as well as some collaborators we had from MIT. And the goal here is to incorporate a differentiable physics model as an implicit layer, as one of these implicit layers in a deep network. Many tasks that we want to reason about physical things, this seems like a good idea, and we're going to build one of these physical simulators and enforce that our network has to incorporate these things. So, as I said, the question about how you do this is, how do I build a physical simulator that I can actually differentiate through this implicit model form? Let's see. So, okay. So that's pretty clarifying things. Okay. All right. Fantastic. So there really are so actually opening up the black box a little bit more from that simple kind of, one equation I had there. Let me actually describe how you formulate physics as an implicit equation. This is sort of the main question, right? Is that, okay, you said that everything can be done as sort of specifying some nonlinear equation you want to solve. How does physics fit into that? So I'm going to show you how to do that. I'm going to show you how to express equations of motion as a certain type of implicit equation called linear complementarity problems. Then I'm going to show how to sort of what this looks like in a little bit more detail when you apply that implicit function theorem to compute derivatives of that linear complementarity program. And then I'm also going to show you how actually you can do this efficiently. So if you noticed in the last slide there was a sort of a big matrix inverse that was involved, and you actually don't want to necessarily always use that matrix inverse, or you want to exploit previously computed versions of that and things like this. So these are really the 3 steps to creating these differentiable rigid body dynamics. Again, there's some math here, but hopefully the high level still comes through. This is how you incorporate constraints like rigid body dynamics into a deep network. All right, so let's start off things. First of all, how do we express sort of the basic laws of physics? So to be clear, this is Newtonian rigid body dynamics. So it basically says that how governing how rigid bodies interact. So you have things like friction, you have things like collisions and stuff like that. And basically, this involves essentially Newton's law. So these are accelerations and mass tensors equal forces, both external and internal forces. That's the governing equations. But to break that down a little bit more, there actually are 3 sets of equations that are involved here. The details here are not actually meant to be at all important. They're more just like writing the math, just so I want to actually put some equations here for what actually is. I mean, it's no more complex than this. This is actually what's going on here. But just to sort of give some view here, the first one, these equality constraints here that govern the system govern things like joints. So constraints that have to be enforced between 2 objects, or one being rigidly attached to another. This next term here, there are basically 3 sets of constraints. The next one incorporates contact constraints. Basically, things cannot interpenetrate, objects can't interpenetrate. And the third one incorporates friction. So when 2 objects are touching, there's certain static friction that kind of governs these things. And these sort of C terms here are what are called complementarity conditions. It basically means that the product of 2 equations, they both have to be positive and their product has to be 0. Again, details are not important here. The high level point here is that these equations of motion, the way you can compute kind of the time derivatives of the dynamical system involves 2 types of equations. It involves equality equations, representing basically, how forces are applied and joint constraints, as well as what are these sort of complementarity conditions that enforce things like contacts and friction and stuff like that. So that's the high level there. And now that we have these constraints, we actually can write down these Newtonian physics basically as a set of combined equality and inequality constraints. And so, we've gone from this sort of, relatively high level notion like physics to actually some equations that govern physics here. And that's really all we've done so far. And they are of this form as what's called this LCP. And it turns out this form here, again, the details are not at all important about what this form actually is. But the point here is that this form is exactly an implicit equation with respect to the inputs and outputs of the system. My Zoom is telling me my internet connection is unstable, which means I'm probably breaking up in the video and audio right now. Hopefully that will rectify itself. If you miss anything, type in the chat and I'll try to get back to it. So what you do is you actually take matrix differentials. This is actually just applying that sort of derivatives through the system there, and then you can kind of go from there and get your Jacobians that way. Again, details aren't important. The important thing is exactly what we had before holds here. So these end up being linear equations in the unknowns. So the unknowns actually in this case are sort of both the dual constraints and things like constraints, as well as your accelerations of your system. And we can solve for all these necessary Jacobians by solving these linear equations here. Now, the thing I actually want to emphasize here is that this is not as maybe inefficient as it first seems upon first glance. So when you first look at this, you say, okay, to compute backprop, if for those that sort of following and sort of have done some implementation of deep networks and sort of think about what can we do here, this seems kind of inefficient. It turns out that to do backprop, you actually don't need to be able to compute actual Jacobians. What you have to be able to compute is something called a Jacobian vector product. And this is actually you just need to be able to multiply by the Jacobian efficiently to do backprop. It turns out that almost always, and this is actually holds true for not just for this example here, but really for most of these implicit model formulations, that if we solve the system to begin with in the forward pass, so if we have to solve the physical system to even get a forward simulation, then this same solution procedure leads to an identical or very similarly inspired backward pass as well. So it almost always is the case that essentially backprop in these systems is either free in some cases if you say compute an exact solution with a matrix inverse, but even if you don't do that, it's essentially the same cost as forward computation. So it's not as if sort of making these things differentiable here is a big cost to the system. It turns out that a lot of these sort of physics engines that already exist out there can actually be made differentiable very easily. And there's been a lot of, this is now actually a few years old, there's been a lot of follow-on work since we did this and concurrent work as we were doing this on building similar differentiable physics engines. Though there was one question about sort of our code being available. Yes, our code is available. It's relatively simple here. It's sort of 2D code, meant for simple simulations, but it is available kind of as an instructive guideline for how we kind of do this. Okay, so that's sort of enough of the details about how we do the math here. Let me sort of pop back out and talk about what we could do with this. So I'm going to give, to be clear, sort of simple examples here. I guess the tie-in to climate science for this part is still a little bit more sort of aspirational than what experience we ran here. But I want to show some simple examples of sort of Newtonian physics integrated in deep networks that accomplish sort of interesting things. So the first one is sort of simple things you can do, like you can do simple system identification. So if you have some system, this is actually not even really deep learning at all. It's just sort of you can identify parameters of a physical simulation from observed data. So say you observe something like this, you observe some, let's see how this plays. And hopefully that comes through in the Zoom. So you sort of have some ball that has a change or something like that. And you observe what happens, and then it evolves according to physics. If you observe that and sort of set up another simulation where you don't know the parameters, say the masses of the chain, I guess you can't not know both. That is undefined. But if you know the mass of the ball, which is not the thing it's interacting with, and want to estimate this. You can do things like run gradient descent, starting with some initial guess for the masses, and after that was a very inaccurate simulation, right? That didn't really behave like the first one. But after a few different sort of steps, you get something that behaves more and more like the actual system you care about. So that's the first one. We just start adjusting the mass of the chain now with gradient descent, and eventually, it maybe not obvious that this is the same thing, but basically eventually you get something that looks very similar to the original system And this is actually a very generic tool here. Anytime you have some physical simulation that you want to fit to data, if you design it to be, if you design a physical simulation in a differentiable way, you can actually do gradient-based system identification, which is oftentimes much more efficient than trying to match your system in other ways. This can be a very sort of powerful tool. Of course, there's no deep learning here, right? This is not actually, there's no real network here. It's just a simple system you're simulating. So I want to give one more example here, or well, another example here, which talks about a little bit more classical deep learning setup, which is predicting dynamics from visual data. So say I observe some balls, some billiard balls bouncing around. I want to use a deep network to predict what the evolution of those things was going to be. This is actually very hard for most deep networks. If you do this with a normal deep network, it'll get them right in kind of the very short term, but it'll kind of then, the balls will start like smearing out and covering the whole space and expanding like a gas into the whole domain, unless you constrain things, at the pixel level to be somehow very, very constrained. And so this is what we do here. And so actually we incorporate some, oops, I guess the first one isn't playing the animation here, but the second one is. So what this is showing here is this is actually showing a prediction made by our model. And what our model does is it first uses a normal deep network to encode the positions of, the visual image to positions of the actual balls, uses our physical simulation to simulate that forward, and uses a decoder on the other end. But the point here is this whole thing is trained end to end. We don't train each part separately. We train the whole thing in an end-to-end fashion, so that we're just basically predicting images from input images, but doing it in a way that's constrained by physics. And so what you get is these dynamics that much more capture sort of the actual evolution you would expect, modulo the weird artifacts you see due to encoder-decoder architectures. Clearly the underlying simulation there is actually capturing real dynamics. And we can kind of show that this also works much better than like a MLP baseline or things like this. And and as we incorporate more and more unsupervised data, it actually helps. The last one I'll show is a similar thing done with Breakout. So we can do a lot of games. I know I motivated this all by not talking about games, but I guess I'm going to come back to games for a second here, because the way Atari games, for example, right now are solved is actually quite it's quite data intensive, right? You need a lot of data to learn how to play even a simple game like Atari. Say versus a human, right? Humans can learn Atari very, very quickly, or Breakout very quickly. Breakout's the one on the right here. It's the one where you move the paddle to break the balls on top. And basically what we do, this is actually at its foundational level, this is a physics game, right? You're bouncing a ball around to knock bricks down. And so we can apply our physics model to this data to learn much more quickly than traditional deep networks can. Just to give a sense of how this works, or the sense of the advantages, double Q learning, which is a reasonable baseline for Atari, does quite well, actually. It can eventually achieve a very high reward here, but it takes about 10 million steps between when it can start getting any reward at all. Whereas our approach, if you just incorporate actual physics into the system, which to be clear is giving it much more information than Q learning has, right? Q learning does not know anything about physics, but if you tell it that there are objects and these objects obey physics and just learn from there, this thing can learn much quicker and actually can develop a policy that well outperforms humans using about only 1,000 observed frames of the data instead of 10 million. So it's many orders of magnitude faster. Yeah, so Justin asks, does the layers before the solver learn a feature representation of the input data that matches the input format of the physics simulator? Yeah, so there are tricks to that. That's a great question, right? So the question I think was for that you actually have a physics inside your network. What guarantee is there that these things will actually match up? That you will actually be able to incorporate to learn a representation that works for the physics simulator. So again, I'm going to be unstable internet connection thing. It happens at the worst times always, but hopefully I'm still coming through here. So there are two answers here. The first answer is that in this example, we gave it a small amount of supervised information about sort of like, here are, I think, like 5 frames or so where this is in fact the position, so that we gave it some grounding. But the bigger thing here is that in this case, we most of the data that we give it is is unlabeled. It's just the input and output image. And just from that, it's able to sort of leverage that data to better improve its representation. I'll say one more thing though, because you actually, in subsequent things, we've actually been able to sort of remove that requirement here. And so what actually happens a lot of cases is that because your sort of bottleneck layer is solving an explicit problem, in some sense, the only way to leverage that explicit representation is to learn the right representation for your hidden layer, right? So it wouldn't be very useful, your physics simulator wouldn't be very useful if it didn't actually learn an underlying representation that's grounded in the input-output mapping of that simulator. And so in some sense, the simulator acts as an implicit bias in the network to force it to learn representations that correspond to what we want it to learn. And so it's actually a very powerful bias that really steers the network towards those things. Though in this case, it was more explicit in the case I just showed there. But you can definitely have kind of both aspects of that. Maybe I'll show it doing a little bit of playing Atari in a model-based way, but I guess you sort of know Atari at this point, so I won't. I'll maybe skip over this quickly rather than show this play Atari for a while. Where's my controller here? All right. Okay. So maybe I'll keep going. I only have about 20 minutes left, so let me actually just keep going to the next thing. I'll take questions after this. The next thing I want to talk about is doing a similar thing, but instead of incorporating now physical simulation into the model, to actually incorporate decision-making of some type into the model. And the sort of the motivating factor I want to say here, which I'm talking about sustainability domains here, so I'll talk about some others as well. Now we'll actually have an example of sort of generation scheduling. But a point that I make frequently about machine learning models is that there's often a disconnect between the loss that's used to train the machine learning system and what we really care about. So for example, typically we have some data, we train a machine learning algorithm, and typically we train the algorithm to minimize some sort of internal loss to the data, right? So we minimize like prediction of the next frame, we minimize, the forecasting performance of some model under a least squares error and things like this. The reality though is that when we use these models in the context of some larger system, mean squared error is not the right metric for what we actually care about. What we actually care about is that, we're going to use that model, say a forecasting model, to make some decisions, say, generation scheduling, and then we're going to pay some costs, based upon our maybe overproduction or underproduction and things like this. And so the actual life cycle of a real machine learning system is much more complex than just a mean squared error loss. And so what we'd actually like to do is start to incorporate the actual cost of decision making as our metric for training machine learning algorithms. And that's what we're going to do with this use of implicit models and these implicit modeling frameworks. Okay, so how does this work? Let me give two quick examples here, because the starting point for these things is some work we did a few years ago now, which we built on a lot since then, called the OptNet approach. And OptNet is a method that incorporates a quadratic programming solver inside a deep network. So I think people here may be familiar with quadratic programming. The basic idea is you solve some, you're minimizing over some variable z, and minimizing some quadratic expression subject to some equality or inequality constraints. And in the context that we care about here, our output of the layer is the minimization over some variables where the problem itself, the terms in the problem itself, can kind of be set up by the input to the problem. So maybe the input gives us the constraints on our domain. Maybe the input gives us, the costs associated with different decisions, things like that. And the high level here is that while this is all kind of great, the high level point I want to make is that this sort of generic QP can also be framed in terms of this implicit kind of layer. So it turns out that the conditions that describe the optimality conditions of a quadratic program are called the KKT conditions, and they are exactly a set of nonlinear equations. So these nonlinear equations are the ones that make up now our implicit layer. and they are how we differentiate through them. And I won't go through it again. I think you've seen enough math on these slides already. I'll start to give some examples. But basically, the high level here is that a lot of optimization problems, finding an optimal solution to some problem, can also be given, be framed in terms of an implicit layer. Before I move on, there's one more question here. So it says, practically speaking, would it be possible to use labels from physics simulation engines to train a subnetwork that learns physical dynamics and then plug those subnetworks with frozen weights into larger architecture? So that's a great question. So the question I think kind of relates to, we know that physics simulations actually are complicated. Can we use a network to kind of train a network to mimic a physical simulator and then plug that network into a larger model? And this is a great idea, to be clear. This is also a great thing to try and to do. But I actually am kind of advocating against that here. Right? I'm actually advocating for a slightly different thing. Because while it's true that deep networks work great to mimic physics simulations, in the precise domain that you give them, in general, these things actually generalize quite poorly when they're taken outside of the target domain, right? So when you're given a brand new set of physical constraints, a deep network that's been trained on one distribution is actually going to perform quite badly on some new distribution. And this is evident in all deep networks we do, adversarial examples like this, they come because deep networks are really bad at generalizing outside their domain. And distribution shifting like this are really bad. And so I'm actually advocating kind of for the opposite. I'm advocating to impose physical simulation as a constraint within networks that we know will generalize well, so we have some grounding to reality, kind of no matter what the rest of the network does. And I think that sort of hopefully answers those two questions, because it's great to think about doing these things. And maybe you want to do them for some reason, and if you have a well-specified domain, great. But there are a lot of cases where we know physics and we really want to enforce this, not as something kind of soft, but as a hard constraint within the network. And in those cases, I would say we should just go ahead and do that. Okay, so we can apply OptNet to do cool things like learn hard constraint sets. This is actually an example of it. Learning constraint satisfaction in a linear space. I won't go too much into it. Basically, the idea is, it's traditionally been pretty hard for deep networks to learn hard constraints. And this network actually gives a simple sort of toy example of given supervised inputs of points and then their sort of projection onto a set, we actually can learn that set kind of just from data very efficiently with gradient-based methods. The point, the actual example I want to highlight a little bit more, though, is one actually from Priya's work, which extended this to the setting not just of quadratic programming, but of general stochastic optimization. So stochastic optimization is cases where you have some, some sort of stochastic objectives. So there's some randomness in your objective, which actually characterizes most real-world problems. And the challenge here was a setting where we actually wanted to do energy generation scheduling based upon forecasts of consumption. Of course, forecasts are themselves going to be stochastic things, right? We can't specify exactly how much people are going to consume in terms of electricity, say in the next 24 hours. Well, we actually can predict some sort of range or distribution over likely consumption. And so what we do is we actually use a network to predict that consumption, but we don't train that network to minimize, or actually we compare two objectives. In the first objective, we compare a network that just is trained to minimize, say, the log likelihood of its predictions, or the mean squared error, because these are sort of under a Gaussian model. On the other hand, we also train a network to build a forecaster to minimize the stochastic optimization cost when we use an optimization problem to schedule generation based upon those forecasts. This actually, there's a few steps, it's a little bit complicated here, but again, maybe going back to my, my previous slide here, what we're doing here is we're making a forecast. Based upon this forecast, we are predicting how to schedule generation, and then based upon the actual reality, we either overgenerate or undergenerate, we suffer some cost. And what we want to ultimately do is minimize that cost. This decision-making procedure is framed as a stochastic optimization problem. And so using the work that Priya and others did, we actually can plug that whole module into the network itself and train the network based upon the loss it actually suffers when we use its predictions in this stochastic optimization problem. And just kind of give a sense of how this works, this next slide here shows the green line here shows our TaskNet approach, which is basically this network trained to optimize the end-to-end costs of the system, whereas the red line represents sort of a network trained just to minimize least squares error. And what happens here on the left, I'm showing the root mean squared error of the two different forecasts that we generate. So we're predicting generation over a 24-hour period. It's actually based upon data from the Pittsburgh area. And as you might guess, you know, the farther out you get, I guess there's peak times here, so that's a little bit noisier here. But the farther out you get your predictions get less and less accurate. And then you know, in terms of you can evaluate this in two ways. You can evaluate this in terms of the root mean squared error. It can in terms of kind of the cost you pay as a generator. And in terms of the root mean squared error, actually, the normal network does it quite a bit better. So, you know, a normal network can actually perform quite well here. But when you evaluate this, and so just minimizing root mean squared error, as you would expect, does a good job of doing that. But if instead you train for this other objective, you still actually do pretty well on root mean squared error. So your loss is a little bit higher. At times, certainly when predicting these things. But if you look at the actual task loss, which is the actual cost you pay in generation, the TaskNet, the one trained to minimize your end-to-end cost of the system, does much better than the alternative approach of just training your system to minimize some simple prediction objective. And this is actually a very, I think, powerful paradigm, going beyond just training networks to minimize the usual losses we think about, actually minimizing what we care about. Now, I'll just say one last thing here, which is that these are sort of, you know, this whole work there is very nice. If you want to go and do it yourself, our code is all available, but it can be quite complex sometimes to implement some of these things yourself. It can, you know, you have to put programs in standard form. You have to figure out the actual, you know, standard form definition of QPs and stuff like that. It's kind of a pain. So I just want to highlight some work we've done recently on making this whole process much easier, which I hope will actually encourage many people here to try these things out and see if they can incorporate these ideas into your own work. And the idea here is that we're actually going to leverage the same tools we use to solve convex programs. So there's many of these packages out there. The one we're going to talk about here is a package called CVXPy, which basically are ways you can easily encode, you know, complex problems in kind of human readable, easy Python examples. So CVXPy is a tool developed out of Stanford, and it's a very nice kind of modeling framework. I'll get to the question there in a second, actually. What we've done in some of our recent work here, so I actually have the citation here. This is work with several colleagues or several collaborators at Stanford that actually work on the CVXPy tool, is that what we've done is we've built a fully differentiable version of this CVXPy tool. And what that means is you can actually write optimization problems in a modeling language like CVXPy, and then you can immediately get from these optimization problems a TensorFlow or a PyTorch layer that will solve that problem in kind of a forward pass of your network, and then backprop through it in the backward pass. So I just really want to highlight here this repository here that we have. Now let's do these things very sort of in a very cool way. So you can basically create a problem in a modeling language like CVXPy. You can create a layer, and then you can backprop through that layer like you would any other sort of PyTorch or TensorFlow layer. What this lets you do, hopefully, is it lets you much more easily, in a way you're kind of familiar with, incorporate these optimization solvers as part of your deep learning models. In a way that's hopefully much more user-friendly than trying to, you know, mess with getting programs into their canonical standard form and things like this. So if you're interested in these things, I would encourage you actually, despite the fact that I have, you know, this code for all this in our various GitHub repos, I would actually encourage you to first see if this fits your needs, because this is a much more user-friendly and kind of easy to use tool that I definitely encourage people to look at as you think about these sort of end-to-end training ideas. Okay, so with that all being said, I've sort of spoken for a while now, and I did want to wrap up to have a little time for questions at the end. Some final thoughts. I think I've made these points now, so maybe I'll make it again because I've sort of made them already in my answering questions for people. But machine learning models have accomplished some amazing things recently, and that were all kind of. I mean, I work in the field, and I'm still kind of shocked and awed sometimes by just how powerful these things can be in certain cases. But they also kind of fail miserably in other cases, right? Including in domains that we really actually understand quite well, that are governed by well-known laws of physics or other physical principles or decision-making systems that have clear objectives to them. The thing I would offer is that, or the insight I hope to offer here, is that this notion of implicit layers in deep learning, they actually provide a very compelling mechanism for integrating these sort of complex physical constraints or optimization directly into networks themselves. And so you actually can integrate directly, not through some approximation, but directly integrate physical systems into your deep learning architectures, or optimization problems into deep learning architectures. This is a very powerful paradigm and lets us do a lot of things that generalize better and that also lead to more sort of, I mean, I hesitate to use the word interpretable, but lead to more kind of predictable and understandable behavior from these networks when applied to new and novel domains. This is also a really fast growing area, so I think that there's a lot of interest in this area right now. But there's also a lot of sort of applications that are, I think, really kind of begging for these things to be used, because there are a lot of cases where we need to satisfy certain constraints in our deep learning systems, and we want to be able to do this, to use the power of deep learning and AI toolkits, while at the same time respecting the hard constraints we have on our systems. So thanks again to my collaborators. The papers and code are available at my website, and I'm happy to, in the small time I have, take any follow-up questions. So there was one already, but I can take it. The one I saw already was, have you considered applying your model to simulate physical motion with nonlinear equations, e.g. the wave equation? Yes. So we've actually done some work with, this is under review right now, and not quite on archive yet, but it should be out soon. We've done some work on using the same tools to do CFD simulation, the differentiable CFD simulation based upon Navier-Stokes, which is a nonlinear equation. So the wave equations would be another one that we could do. We've done it largely with CFD models thus far. But yes, definitely, nothing requires these things to be linear. In fact, they actually aren't linear. The complementary conditions and the optimization conditions, those are actually all non-linear equations that we're finding the roots for. And so you can absolutely do it for nonlinear simulation as well, like CFD simulation and others. Yes, so Wyatt asks, with the bias imposed by the implicit physical model, how easy is the model able to improve upon the prediction of the physical simulator? Its ability is a simpler or more complex physical models. This is a great question, and I think so the intuition here is that if we can maybe, with some data from a real system, we can combine a relatively simple model with data to get a predictive model that's actually quite high fidelity on novel new data, instead of, say, using a very high fidelity original model, or maybe it's just capturing things that are fundamentally noisy that we really can't capture in a physical model. This is actually exactly the situation that we are looking at in this recent CFD work, which I didn't talk about here, basically using a very coarse model to do better than a fine-grained model. But it's also true that ultimately we're getting our data from like a very, very high fidelity model. So I think the compelling application of sort of integrating this with the real physical observations we haven't done yet, and it remains to be done still. So can you pinpoint where you think the gain comes from incorporating physics principles, as we know much of the principles are drawn from observations? Yeah, so that's a great question. So this is sort of a philosophical question, right? So if physics is learned from data itself, which I believe on some level, then what's the advantage of it? And I actually think that it's true that physics is motivated by data, but I guess I'm sort of a this is like a philosophical question, right? I actually believe in mathematical laws underlying and governing the universe in some sense. And so I believe there actually is a truth to things like, I guess an approximate truth in Newtonian dynamic sense, but I believe there actually is a truth to these things. If nothing else, they are very compact representations of very good models. And our networks that we learn, they do not learn compact representations of physical simulation. They learn sort of, famously non-generalizable and non-compact representations. And so in some sense, what incorporating physics does, maybe from a philosophical standpoint, is that it's incorporating kind of hundreds of years of our learning and our understanding of how to simplify observed phenomena into our networks without it having to somehow learn that over hundreds of more years of training and data and things like this. Okay, maybe the last question, because I know we're at time, so feel free also cut me off if you want to before that, Priya. The last question says, given that exploring a solution space is expensive, can these methods really shortcut the need for that exploration? I think that's actually kind of a hard question to answer. These are by no means a sort of generic solution. When you have any problem in any problem space, this is going to give you the answer. Of course not. If anything, is actually kind of the opposite. I think oftentimes we view machine learning as kind of this generic black box that tries to solve kind of anything given anything else, right? We try to just give it inputs and hope that in every situation the output it has will be the one we have. The way I would characterize this work actually is this work is about embedding kind of our knowledge and our pre-done exploration into the models in a way that actually forces them to learn things that require less exploration from a modeling standpoint. And so that's how I would kind of characterize this. This is not by any means a tool that will work for any situation. You have to understand your domain, but that happens a lot. There are a lot of cases where we understand our domain and we want to incorporate that information. And so these sort of tools, and I should clarify, many others as well out there to sort of do similar things. These tools help us incorporate that prior knowledge in a way that can actually hopefully better solve these problems.
All right, Zico, thank you so much for that. I think there seem to be questions still coming in.
Should I be cut off now? Yeah.
Yeah. Great. Yeah, thank you so much.
I think I better make some time for the next person and not take much time. Feel free to reach out to me over email. I'll do my best to explain. And if you have outstanding questions, it's wonderful to be here. And thank you, Priya, and all the organizers for setting this up.
Awesome. And yeah, for anybody who wants to use that clap button, as I've heard Zico himself saying, it's never as satisfying as actually getting clapping going. But if you'd like to use the clap button, feel free. Thanks, Zico.